Okay. Welcome to my class. Start.
Hello students, let us discuss today first 3 chapters of first PUC chemistry. So let us begin with some basic concepts of chemistry. We will see some important concepts which will help for your competitive exams. So significant figures, rules. All non-zero digits are significant. Zeros preceding the first non-zero digit are not significant. Zeros between two non-zero digits are significant, and zeros at the end of a number are significant when they are on the right side of the decimal point, and counting numbers of objects have infinite significant figures. Next we will move on to scientific notation. Now when we have very big number or very small number, we express such numbers in this form. That is, here n is digit term and this n is exponent having positive or negative value. Now we have consider a number line. Here we have 0, to the right of this we have positive numbers, and to the left of 0 we have negative numbers. Now to write this in terms of scientific notation, if we put the decimal and go towards the left, 1, 2, 3, 4, 5, 6, 7. Now we are writing this number as 1.254 into 10 to the power 7. To keep this in mind, on the number line, if we move towards left, the numbers we are getting is negative, but the exponent term will be positive. Similarly, for this number, decimal, if we shift decimal to the right side, 1, 2, 3, now this can be written as 4.56 into 10 to the power minus 3. Again, on the number line, if we go towards right side, we are getting positive numbers, but in scientific notation we put negative exponent. So that is scientific notation. Now significant numbers in answers involving calculations. Now while doing calculation, the result of an addition or subtraction should be reported to the same number of decimal places as that of the term with least number of decimal places. The number of significant figures of different numbers have no role to play. Next we will see some of the important formulas of this chapter. Molecular formula is equal to empirical formula into n, where n is a number. Now molecular formula gives us the actual number of atoms present in a molecule, whereas empirical formula gives ratio of different atoms present in a molecule. Now molecular mass is equal to n into empirical mass, and similarly molecular weight and vapor density relationship is 2 into vapor density is molecular mass. Now to calculate the strength of a solution, we can use some of the formulas, like this is a normality equation, N1V1 is equal to N2V2. To dilute a solution and to find out the strength of that diluted solution, we can use this formula. For dilution from volume 1 to volume 2, or exact reaction between solutions of two reactants can be given by this formula. Molarity equation is M1V1 is equal to M2V2, which can be used for diluting solutions. Now M1V1 by N1 is equal to M2V2 by N2 for reactions where N1 and N2 are number of moles of two reactants in balanced equation. NA-MaVa is equal to NB-MbVb, where Na is basicity of the acid, NB is acidity of the base. Now, if we have two solutions, say first solution with strength N1 and volume V1, second solution with strength N2, volume V2, if we mix these two, we get a new solution whose strength can be represented as N3, then it can be found out by this equation. So, volume V1 plus V2 into N3, by this we can find out the strength of the resulting solution. Similarly, if molarity is used, M1V1 is equal M1V1 plus M2V2 is equal to M3 plus M3 into V1 plus V2. Now, basicity is the number of displaceable H plus ions present in one molecule of the acid. So, that is basicity, number of displaceable H plus ions in one molecule of the acid. Example, if we take HCl, the basicity is 1, H2SO4, basicity is 2, H3PO4, basicity is 3. Similarly, for the base, acidity is the number of displaceable OH minus ions present in one molecule of the base. If we take any OH, acidity is 1, CaOH twice, acidity is 2, AlOH thrice, acidity is 3. Acidity is 3. Next, what is mole? Mole can be defined in different ways. First definition we will see in terms of mass. Mole is defined as the amount of the substance which has mass equal to gram atomic mass. If the substance is atomic, or it is gram molecular mass if the substance is molecular. So, mole is defined as amount of the substance which has mass equal to gram atomic mass or gram molecular mass, depending on whether it is atomic or molecular. Now, example we will take. One example we will take 1 mole of oxygen atoms. 1 mole of oxygen atom means 1 gram atomic mass, that is 16 gram, because atomic mass of oxygen is 16 U. So, 16 gram of oxygen is 1 mole of oxygen atoms. One more definition in terms of number. Mole can be explained in terms of number. A mole is defined as the amount of the substance which contains Avogadro number. Avogadro number is 6.022 into 10 to the power 23 of atoms if the substance is atomic, or this much molecules if the substance is molecular. Now, specifying the particle, that is very important. 6.022 10 to the power 23 atoms or 6.022 10 to the power 23 molecules, depending on whether the substance is atomic or molecular. Now, for this we will see the example. Again we will take oxygen itself. 1 mole of oxygen molecules, 1 mole of oxygen molecules, again it contains 6.022 into 10 to the power 23 molecules of oxygen. If we take 1 mole of oxygen atoms, same number of atoms, oxygen atoms are present in that. This is just like a dozen. Dozen contains 12 numbers, and we have to specify which particle we are taking in dozen. But the number have mass different. Here we have this much number of atoms of oxygen, mass is 16 gram, and this much number of molecules of oxygen, this is having 32 gram mass. we'll move on to another definition, that is in terms of volume. In case of gases, a mole is defined as that amount of the gas which has a volume of 22.4 liters. This is in terms of volume. Again, same example we'll take. If we take 1 mole of oxygen gas, it occupies 22.4 liters of oxygen at STP. 1 mole of oxygen gas is 22.4 liters of oxygen at STP. So, this is in terms of volume. Next, we will see some of the concentration terms of the solution. Mass by mass percentage. Now, mass percentage of the solute is mass of the solute by mass of the solution into 100. Mass by volume percentage is amount of the solute in gram present per 100 ml of the solution. Volume by volume percentage is given as, that is volume by volume percentage of solute. If we take volume of the solute by volume of the solution into 100. Since it is percentage, so it is 100. Next, one more concentration term is parts per million, which is denoted as ppm. That is mass of the solute by mass of the solution into 10 to the power 6 million. Mole fraction. Now, mole fraction of A is number of moles of A by total number of moles. Number of moles of A, the component A, divided by total number of moles. If the solution is having 2 components, in denominator we have sum of the moles of 2 components. Similarly, mole fraction of B is NB by Na plus NB, or mole fraction of A and mole fraction of B together is equal to 1, and by this the mole fraction of unknown components mole fraction can be found out by this equation. Next, molarity. Molarity is number of moles of the solute by volume of the solution in liter. Volume of the solution in liter, whereas molality is number of moles of the solute by mass of the solvent in kg. Number of moles of the solute by mass of the solvent in kg. Now we will move on to stoichiometry and its calculations. Stoichiometry is the calculation of quantitative relationships of the reactants and products in a balanced chemical reaction. Quantitative relationship of the reactants and products in a balanced chemical reaction. So what is limiting reagent? The reactant which reacts completely in a reaction is limiting reagent. The reactant which reacts completely in a reaction is limiting reagent. We'll move on to next chapter, structure of atom. Now, subatomic particles and their properties we will see, some fundamental particles. Electron, charge, electrons and protons have same charge with opposite sign, and neutron has 0 charge, no charge, neutral it is. Relative charge, electron is represented as -1, this with +1, it is 0 for neutron. and mass per kg for electron, proton, neutron, and approximate mass is written like this. Now some of the atomic terms we will see. Atomic number, which is denoted by Z, which is nothing but number of protons or number of electrons of a neutral atom. Neutral atom. Now mass number is denoted as A, which is total number of protons and neutrons in an atom. Total number of protons and neutrons in an atom. Nucleon is protons and neutrons present in a nucleus. So these fundamental particles are collectively known as nucleon. Isotope, iso means same, topos means place. So atoms of the element with same atomic number, because place is given based on the atomic number. So atoms of the element with same atomic number but different mass number. But different mass number. So example, if you take 1H1, 1H2, 1H3, the isotopes of hydrogen. One more term, isobars, atoms having the same mass number but different atomic numbers. Mass number is same but atomic number is different. Example, we can take this as example. Next, isotones, atoms having same number of neutrons but different number of protons or mass number. Same number of neutrons, different number of mass number. That is isotone. Next, isoelectronic, again same electrons. Same electrons. Now atoms, molecules or ions having same number of electrons are isoelectronic species. Next, nuclear isomers. These are the atoms with the same atomic number, same mass number, but with different radioactive properties. Different radioactive properties. Now for this, example can be given as uranium X, uranium Z with different half-life period. Next, isosters, molecules having same number of atoms and also same number of electrons are called isosters. Same number of atoms and same number of electrons. 2 atoms here, 2 atoms here, electrons 14, here 6 plus 8, again it is 14. These are called as isosters. Now, if we take a neutral atom, it can be represented like this, where Z is atomic number, A is mass number. So number of protons is equal to number of electron, which is equal to atomic number. If we take a negative ion, here the charge is written. Here in this case, number of electrons is greater than number of protons. So the ion gets a negative charge. Now number of electrons is equal to Z plus N. If we take positive ion, positive charge it has, so it is positive ion. Number of electron is less than number of protons. So it gets positive charge. Number of electrons can be calculated as Z minus N. Now, however, number of protons is always Z and number of neutron is always, now if we denote a an atom like this, Z is number of protons, that is atomic number. Neutrons number can be calculated as A minus Z. This is the number of neutrons. Next, some terms explanation we will see. Wavelength, lambda is distance between two neighboring throws or crests, that is wavelength. Frequency nu is number of times a wave passes through a given point in a medium in 1 second. That is frequency. Frequency is given by the formula nu is equal to c by lambda. Velocity, the distance travelled by the wave in 1 second is velocity. C is equal to nu lambda. Wave number, nu bar, is number of wavelength per centimeter. Amplitude, it is height of the crest or depth of the throw, which determines the intensity of the beam of light. Intensity of the beam of light. Next, one more formula, de Broglie equation, which can be written as lambda is equal to h by mv, where mv is momentum. It can be written as h by p also. Lambda is equal to h by p, momentum. One more principle is Heisenberg's uncertainty principle, which defines it is impossible to determine simultaneously the exact position and exact momentum of an electron. So simultaneously we cannot find out the position and momentum of an electron. So mathematically it can be written like this: delta x into delta v is greater than or equal to h by 4 pi m, or you can write it as delta x into delta p is greater than or equal to h by 4 pi. H by 4 pi. Next, we will move on to quantum numbers. Now, quantum numbers are the numbers which are used to locate the electron. We have 4 quantum numbers. Principal quantum number denoted by n, which has the value 1, 2, 3 and so on, which explains the shell in which the electron is present. Azimuthal quantum number can have value from 0 to n minus 1. So always azimuthal quantum number is lesser than principal quantum number. This defines the subshell of the electron. So if we have 0 value for the azimuthal quantum number, the subshell we get is S. 1, 2, 3 L values means respectively we get P, D, F subshells. Now, one more quantum number, magnetic quantum number, can have values minus L, 2 plus L through 0. This is the value of magnetic quantum number. If we know n, we can calculate L. If L is known, m can be calculated. And when comparing L and m is equal to plus or minus L, or it can have 0 value also. Next, spin quantum number can have 2 values, plus half, minus half, whether the electron revolves in the clockwise direction or anti-clockwise direction. Now magnetic quantum number value gives us the number of orbitals present in a subshell. The number of orbitals present in a subshell is 2l plus 1. Each orbital can accommodate 2 electrons, so the number of electrons present in a subshell is 4l plus 2. 2n square is the maximum number of electrons in a shell. Next we will move on to atomic spectrum of hydrogen atom. Now if we take hydrogen gas in a discharge tube and subject it to electric discharge, the molecules are converted to atoms and atoms emit radiations of discrete frequencies. By this we get spectrum of hydrogen, line spectrum of hydrogen, where the spectrum contains a series of lines. These lines are classified into different spectral series and they are Lyman, Balmer, Paschen, Brackett and Fund series, for which the value of N1 is 1, 2, 3, 4, 5 respectively, and the value of N2 is N1 plus 1, N1 plus 2, and like that it continues. The spectral region for different series of lines are UV, visible and infrared region. Now if you keep the series names in this order, you can keep this value also in your mind easily, 1, 2, 3, 4, 5, it continues like that. Now wave number of each line can be calculated by this formula. Nu bar is equal to RH 1 by N1 square minus 1 by N2 square, which is equal to 1 by lambda. Nu bar is 1 by lambda, where R is Rydberg constant and N1, N2 are integral numbers. Now the frequency nu of the photon of light emitted depends on the energy difference of the two energy levels and can be given by the expression. Now first energy level, the energy is denoted as E1. For the second energy level, if we denote it as E2, then delta E is E2 minus E1 is H nu, or nu is equal to E2 minus E1 by H, where E2 is the energy of the higher energy level and E1 is the energy of the lower energy level, and H is Planck's constant. Now frequency is related to the wavelength as nu is equal to c by lambda, where c is the velocity of light, or we can write the equation like this. Now orbital is a region where the probability of finding the electron is maximum, and in orbital we get a region where probability of finding the electron is 0, which is called as node. Now number of spherical or radial nodes in any orbital is given by the formula n minus l minus 1. Number of planar or angular nodes in any orbital is given as L. Total number of nodes then becomes L is equal to total number of nodes in any orbital is n minus 1. Next we will see some of the important formulas which are related to hydrogen spectrum. Now energy absorbed or released in an electron jump is given by E2 minus E1, which is equal to h nu. Energy of stationary state of hydrogen atom is minus RH into 1 by n square. For hydrogen-like species, Hydrogen-like species means helium plus, lithium 2 plus with atomic number Z. Radius of nth orbit becomes 52.9 into n square by Z picometer. Energy of nth orbit is minus 2.18 into 10 to the power minus 18 into Z square by n square. This is in joules, or in terms of electron volts it becomes minus 13.6 into Z square by n square. Energy of the nth orbit. Next we will move on to isoelectronic series. Now isoelectronic means the species which have same number of electrons. Now here it is O2 minus 10 electron, 10 electron, 10 electron. Here also all these species have 10 electrons. Now you can compare the size. As the negative charge increases, size also increases. As the positive charge increases, size decreases if the species are isoelectronic. Now, if we consider a neutral atom, its negative ion and its positive ion, then the negative ion is larger than the neutral atom and positive ion is smaller than the neutral atom. Or else you can get the size as ionic radius is proportional to 1 by atomic number. Ionic radius is inversely proportional to 1 by atomic number. By the picture you can have a clear idea of size of the isoelectronic species. So we'll move on to next chapter. Classification of elements and periodicity in properties. Now modern periodic law states that properties of the elements are periodic function of their atomic numbers. We'll see the classification of elements. Elements are classified into different blocks depending upon the differentiating electron, presence of differentiating electron in different orbitals. So in S block we have the last electron in S orbital. In P block we have last electron in P orbital. Similarly in D and F the last electron is present in D and F orbitals. Now for S block elements, the valence shell electronic configuration can be written as NS122 and nature is metals. First and second group elements belong to this block. For P block elements, NS2, NP 1 to 6. These are metalloids, non-metals and some of them are metals also. Group 13 to 18. D block elements, group 3 to 12 and the electronic configuration is N-1D 1 to 10, NS 1 to 2. They are, most of them are metals and we have here 3D, 4D, 5D series. In the F block elements, the outermost electron enters F subshell and electronic configuration can be written like this. They are radioactive. 4F series are lanthanoids, 5F series are known as actinoids. Next we will see periodicity in atomic properties. We have different periodic properties of the elements. Out of that, first we explain atomic radius. Atomic radius, as we move from left to right, atomic radius decreases, whereas from top to bottom atomic radius increases. All other properties increases from left to right and decreases on moving from top to bottom in a group. Now, ionization enthalpy. The energy required to remove outermost electron from an atom is known as gaseous atom is known as ionization enthalpy. Now, this is the diagram which shows variation of first ionization enthalpy. Variation of first ionization enthalpy, where ionization enthalpy versus atomic number graph is drawn. This is first period, we have second period, third period, like that. And at the top we can see noble gas elements. So in each period, noble gas elements are having highest ionization enthalpy because van der Waals force exists in them. Now we see some variations in each period that can be explained like this. Now the first ionization enthalpy of elements of the second period. Now here second period elements are taken. In the periodic table, general trend of ionization enthalpy is from left to right, ionization enthalpy increases. But here beryllium is having, so first we get beryllium, after that boron comes. So according to general trend, boron should have higher ionization enthalpy than beryllium, but in practice beryllium is having more ionization enthalpy than that of boron. This is because here we find completely filled orbital. Similarly here, nitrogen, oxygen according to the general trend, oxygen should have more ionization enthalpy when compared to nitrogen, but in nitrogen half filled orbital is available, so which is stable, so removal of electron from here is difficult, so energy is required is more than that of oxygen, so that is the exception. Similarly, alkali metals, first group lithium, sodium, potassium, rubidium, the variation is shown in the graph. Now electronegativity values based on Pauling scale across the period. For lithium it is 1, 0.5 increases as you go from left to right. So that is the value of electronegativity based on Pauling scale. Similarly, this is for first group elements. Next, we will move on to question part. We will discuss some of the questions from previous year question papers. You have to practice more questions so that we will get clear idea to solve any type of questions. So first question, an organic compound contains 80% by weight of carbon and remaining is hydrogen. So carbon percentage is 80%, whereas hydrogen is 20%. Before that we will see the options. Now atomic mass is given, it is 12 for carbon and 1 for hydrogen. Now percentage composition is divided by atomic mass. So here you get 6 times 6.6 something you get, and here it is 20. Now select least number and get the ratio. 6.6 it is 1, 6.6 20 by 6.6 is 3 point something, we are getting 3.3 something. Now this is carbon ratio is, this is hydrogen, so it is C1H3, so the answer is A. So option A is the correct answer. We'll move on to the next question. The number of significant figures for 3 numbers. 3 numbers are given. Easily you can do this. So answer, we'll check the options 3, 4, 5. For this, non-zero digits are significant. 3. Now here also the 0 to the left is not significant, so here also we get 3, and here also we are getting 3 significant figures. So this should be the correct answer. 3, 3, 3. So first all non-zero digits are significant. So 3 we are getting in that case. Non-zero digits to the right of the decimal point are significant. So we are getting 3 significant figures. Zeros to the left of the first non-zero digit in a number are not significant. This is not significant. So that is also 3. So answer is D. Next we will move on to the number of radial nodes in 3s orbitals. We'll see the options. It is 1, 2, 3, 4. Now radial nodes, formula is n minus L minus 1. Now for this orbital, the value of n is 3. To get s orbital, L should be 0, 3 minus 0, minus 1, which is 2. So the option B is the correct answer. Next question. The number of protons, neutrons and electrons in 71 Lu 175 is, options we will check. Now the first it is proton, should be proton, then neutrons, then electrons. Now since the element is given, this is atomic number, number of protons and number of electrons. So 71 we have to check. 71 is here, 71 is here, but 71 here. So this should be the correct answer. You need not count this number, but we will count that also. So here different number is there. Here 71 is here, but here different number is there. So this is wrong, this is wrong, this is also wrong. So this is the correct one. So calculations if you want. Mass number is, this is mass number 175, which is number of neutron plus proton. Atomic number, this is atomic number Z, 71. Proton number is equal to electron number, both same. Number of proton is 71, number of neutron is A minus Z. A is 175, Z is 71, so number of neutron is 104. We have 104 in the middle, so that is the correct answer. Next question. An element X has the following isotopic composition. X200 is 90%, X199 is 8%, X202 is 2%. The weight average atomic mass of the naturally occurring element X is closest to, we have to calculate the average atomic mass is to be found out. Options we will see. Average atomic mass is found out. How to find out? That is percentage composition into mass number. Percentage composition into mass number. 90% is 0.9 into 200. 200 is this. We get this much. Second one, that is 8%. 8% is 0.08. That is 8 by 100. This is 90 by 100. 0.08 into 199. 199. Answer comes around 15.92. And the third one, X202, 2%. 2% is 2 by 100. That is 0.02 into 202, which comes around 4.04 U. On adding these three, total weight is approximately 200 U or 199.96, which is approximately 200 U. That is answer D is the correct one. Next we will move on to next question. How many electrons can fit in the orbital for which n is 3 and L is 1? if n is 3 and L is 1, we get the orbital 3p, and p subshell can accommodate maximum of 6 electrons. P subshell can accommodate maximum of 6 electrons, that is P, S, P, D, F, here 2, 6, 10, 14 are the maximum number of electrons present. Next, 1 mole of carbon atom weighs 12 gram. The number of atoms in it is equal to, we have to find out the number of atoms in 12 grams of carbon. 1 mole of carbon mass is 12 gram. We know that 1 mole contains Avogadro number of carbon atoms. So 12 gram contains 6.022 into 10 to the power 23. This is the value of Avogadro number. This is the correct answer. 1 mole of carbon atom weighs 12 gram. It contains Avogadro number of carbon atoms, that is 6.022 into 10 to the power 23 number of carbon atoms. So answer is D. We'll move on to next question. Which is the correct order of increasing energy of the listed orbitals in the atom of titanium? Now we have to arrange the orbitals in the increasing energy order. So the orbitals are arranged in the increasing order of energy based on n plus L rule. Now we will calculate for these orbitals n plus L value. N value, L value, we will calculate for 3s. We have 3s, 3p we have, 3d we have, 4s we have. Now for this, n is 3, L is 0, n is 3, L is 1, n is 3, L is 2, n is 4, L is 0, n plus L is, this is 3, this is 4, this is 5, this is 4. So the order is, this should come first, then comes this. Now these two are having same value. Now the orbital with lower n value is having lesser energy. So that is 3s, 3p, 4s, 3d. This is the order of the orbitals in the increasing energy. So the option is D. Next question. The number of moles of hydrogen molecules required to produce 20 moles of ammonia through Haber's process is. Let's check the options. So 20, 30, 40, 10 are given. Now, in Haber's process, the ammonia can be prepared like this. Now from the equation, for 2 moles of ammonia, we require 3 moles of hydrogen. Now 1 mole of ammonia can be prepared by 3/2 moles of hydrogen. This is by the equation we have. Now we'll move on to the equation. The question is, the number of moles of hydrogen required to produce 20 moles of ammonia. We want to prepare 20 moles of ammonia. How many moles of hydrogen is required? We have to find out, and that is 20 into 3/2 2 ones are 2 tens are, which is 30 moles. 30 moles is the answer, and B is the correct option. So according to Haber's process, we have N2 plus CH2 gives 2 NH3. Now 2 moles of ammonia require 3 moles of hydrogen. Therefore 1 mole of ammonia require 3 by 2 moles of hydrogen, or 20 moles of ammonia require 3 by 2 into 20 moles of hydrogen, that is 30 moles of hydrogen. B is the correct option. We will move on to the next question. The first emission line of the hydrogen atomic spectrum in the Balmer series appear at, the options are per centimeter unit it is given. So we have to calculate the first emission line of hydrogen atomic spectrum in the Balmer series. Since the unit is this, the formula to be used is R into 1 by N1 square minus 1 by N2 square. The series given is Balmer series, N1 is 2 and the line required is first line required is first line, so N2 is 3. This is 2 square, 3 square. Now on simplifying, this is 1 by 4, 1 by 9, which is 4 into 9, and here it is 9 minus 4, which is 5 by 36, R is there, 5 by 36, which is 5R by 36 per centimeter, 5R by 36 per centimeter. So option is A. So new bar is R into 1 by N1 square minus 1 by N2 square. Here the first line of the hydrogen atomic spectrum in the Balmer series is this. N1 is 2, N2 is 3 for the first line. Next question. Quantum numbers are different quantities used to describe the electrons present in an atom. Each quantum number signifies a property. Identify the quantum number that determines the orientation of the orbital in space. We'll check the options. And orientation is explained by magnetic quantum number. Orientation of orbital in space is by magnetic quantum number. Now, magnetic quantum number represents the total number of orbitals in a subshell as well as their orientation. So, the answer is C, magnetic quantum number. Now, next question. From the following set of quantum numbers, which state is possible? Which set of quantum number is possible? Among these 4 options we have to check. Now first we will move on. N is 0, L is 0, M is 1. Now when L is 0, M cannot be 1. So this is not possible. N is 2, L is 1, M is 0, this is possible. N is 2, L is 0, now L is 0, M cannot be 3 because for a given value of L, M is minus L, 2 plus L through 0. So this is also not possible. Next, N is 3, L is 1, M is 0, this is minus half, this is also possible. We'll check the option. 1, 2, 3, no. 2 and 4 are possible. This is the correct answer. This. Now the explanation is here. Because of the minimal value of N can only be 1 and not 0. here this is also n cannot be 0 and this is possible. The value of L is 0, then the value of M should start from 0 only, not 3, and this set of quantum number is also possible. So answer is B, 2 and 4 are possible. So we'll move on to the next question. The empirical formula and molecular mass of a compound are CH2O and 60 respectively. The compound is, we should identify the compound with this molecular formula, empirical formula and molecular mass. Now we have a formula, empirical formula mass is equal to molecular mass. Here it is multiplied by some number. Now empirical formula is CH2O, its mass become 12 plus 1 into 2 plus 16 into N is equal to molecular mass is given, which is 60. From this we can calculate N. Here you see it is 12 plus 2, 14, 30. 30 N is equal to 60. N is equal to 60 by 30 is equal to 2. 60 by 30 is equal to 2. Now substitute here. Empirical formula is CH2O into N is 2, which becomes C2H4O2. We will check the option now. C2H4O2 is not there, just will count C1 here, no, wrong. C2H4O2. So this is the correct one. Here we have C6, here we have C4. This is also wrong. So option B is the correct answer. Next we will move on to next question. A hydrocarbon has formula CN plus CnH2n plus 2. If it has vapor density 29, then the value of N is, we should find out now N we have to find out. For that, the options given are 1, 2, 3, 4. Now the formula is, hydrocarbon formula is this much. Now we will calculate the mass of this. 12 carbon, atomic mass is 12, 12 into N plus hydrogen 1 into 2N plus 2. 1 into 2N plus 2. This is molecular mass of this formula. Now this is equal to, now one more formula we have, vapor density into 2 is equal to molecular mass. Molecular mass is vapor density into 2. Vapor density is given 29 into 2, that comes around 58. That is 58. Now this is molecular mass, which is equal to 58. From here you can get N. N is equal to 58 divided by, now this is 12N, 2N, 14N plus 2. 14N plus 2 is, 14N is equal to 58 minus 2 is 56. N is equal to 56 by 14, that is 4. N is equal to 4. D is the correct answer. D is the correct answer. Next we will move on to the next question. The electronic configuration of an element, it is given 1s2, 2s2, 2p6, 3s2, 3p3. What is the atomic number of the element which is present just below the above element in the periodic table. Now, in the periodic table, the elements which are present in a group have same outer electronic configuration. So, the element is having valence electronic configuration as 3s2 Tp3. The element just below this should have 4s2 4p3. That is, in the next period it comes. So, the period number increases by 1. So, 3s2 becomes 4s2, 3p3 becomes 4p3. Now, what is the atomic number is asked. So, we should continue this. This is the outer electronic configuration, and the electronic configuration for this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. In between there comes 3d, 4s and 4p comes 3d, 3d10, 4p3, and it comes 2, 4, 10, 12, 18, 20, 30, 33. We'll check the options. 33 is the correct answer and option A is the correct one. The element which is present just below the given element will have outermost electronic configuration 4s2 4p3. So, the full electronic configuration can be written like this and the atomic number becomes 33. We will move on to next question. So, answer A is the correct one. Now, identify the wrong statement in the following. We will see the options. So, first option is, among isoelectronic species, smaller the positive charge on the cation, smaller is the ionic radius. Smaller the positive charge, smaller is the ionic radii. We have seen this one picture regarding isoelectronic species. The size and charge on the ions are compared there. As the negative charge increases on the ion, ionic size increases. As the positive charge increases, ionic size decreases. Here it is smaller positive charge, smaller size is wrong. This appears as it is wrong. Next one, among isoelectronic species, greater the negative charge anion on the anion, larger is the ionic radius. This is correct. Atomic radius of the element increases as we move down the group in the periodic table. This is also correct. Atomic radius of the element decreases as we move across left to right in the second period. This is also correct. So, option is A is the correct answer. A is the correct answer and the explanation will again check. Atomic radius of the elements decreases across a period from left to right due to increase in effective nuclear charge. On moving down the group, since the number of shells increases, atomic radius also increases. Amongst isoelectronic species, ionic radius increases with increase in negative charge or decreases in positive or decrease in positive charge. So, option A is wrong. While reading the question, you should read it carefully. Wrong statement is asked. A option is wrong. We will move on to the next question. Among the following, the one which is most basic is, we will check the options. Now, ZNO, MgO, Al2O3, N2O5 are given. Now, these two are amphoteric oxides, whereas this is non-metallic oxide which is acidic. This is metallic oxide which is basic. So, the answer is B. B is the correct answer. ZNO, Al2O3, amphoteric oxide. N2O5 is oxide of non-metal, so it is acidic. MgO is most basic among the 4. So answer B is the correct answer. Next we will move on to next question. The number of atoms in 8 gram of sodium is x into 10 to the power 23. 8 gram of sodium contains x into 10 to the power 23 atoms of sodium. The value of x we have to find out. Value of x is to be found out. Given n is 6.02 into 10 to the power 23 mole, atomic mass of sodium is 23 U. Now, this is the atomic mass. So, 23 gram of sodium contains Avogadro number of sodium atoms, that is given 6.02 into 10 to the power 23 sodium atoms, 23 gram contains. Now, 8 gram contains this much, where we have to find out x. So, we will calculate it. This is 23 into x into 10 to the power 23 divided by 8 into 6.02 into 10 to the power 23. Now, we will keep x here, take all remaining terms to the other side, 8 into 6, cancel out this, 8 into 6.02 divided by 23 is equal to x. So, this is 8 6 are 48 divided by 23, which comes around 2. B should be the answer. So, 2 is the answer. So, that is the answer for that question. We will move on to next question. The correct set of 4 quantum numbers for the valence electron of rubidium atom. Now, we have to select the correct set of quantum number for the valence electron of rubidium atom. Now, atomic number is given. You can, from the atomic number, you can get the shell and subshell of valence electron of rubidium, or else you can go, rubidium is present in first group, that is lithium, sodium, potassium, rubidium. From the first group, the valence electronic configuration is NS1. From here also you can calculate, either by writing the electronic configuration completely and getting the shell and subshell of the valence electron, or from the first group electronic configuration you can get the shell and subshell of the valence electron of the rubidium. Now, this is second period, third, fourth, fifth period. Here we have hydrogen in the first period. Now, since rubidium is present in fifth period, this is an outer electronic configuration becomes 5s1. So, for this we have to write the electronic configuration, quantum numbers we have to assign. 5 is the principal quantum number. We have here, here, here. S is the subshell. L should be 0. Here it is 1. No. Here it is 0. Here it is 1. This is also wrong. So, this is the correct answer. 5, 0, 0 plus half is the correct answer. So, this is principal quantum number. S subshell gives us the value of L, azimuthal quantum number. N is 5, L is 0. So, C is the correct answer. Next question. The momentum of a particle having a de Broglie wavelength of 10 to the power minus 17 meter is given. We have to calculate momentum of a particle having a de Broglie wavelength 10 to the power minus 17 meter. So, momentum is to be calculated. So de Broglie equation is lambda is equal to h by p. Now h is given 6.625 into 10 to the power minus 34. Momentum of a particle is to be calculated. Wavelength is given. Wavelength is 10 to the power minus 17. P is to be calculated. We will just write P here. 10 to the power minus 17 here. So the answer comes around. Take this to the numerator. So 6.625 into 10 to the power minus 17, that is minus 34 plus 17. Answer is this much. We'll see the option. And the option, this is, no, this is not the answer. This is 6.625 into 10 to the power minus 17. This is the correct answer. C is the correct answer. We'll check D also. This is plus 10 to the power 17, wrong. So C is the correct answer. Next we will move on to the next question. Maximum number of electrons in a subshell of an atom is determined by the following. Now the number of orbitals present in a subshell is given by 2l plus 1. Now each orbital can accommodate maximum of 2 electrons. So this is the number of electrons in a subshell of an atom, that is 4l plus 2. We'll check the options. So 4l plus 2 is the answer. A is the correct answer. Next question. The first ionization potential of nitrogen and oxygen are respectively given. Some values are given. We'll just see the first ionization potential of nitrogen and oxygen. Nitrogen and oxygen in this order. Question is asked. They exist in second period, and nitrogen atomic number 7, oxygen atomic number 8. Their position in the periodic table is like this, and the general trend is as we move from left to right, ionization potential increases. Ionization potential increases, but here exception arises, that is, this is having half filled p orbital. So from the stable half filled orbital, removal of electron is little difficult, energy required is high. So nitrogen is having higher ionization potential than oxygen. So first ionization potential of nitrogen is more than that of oxygen, and in the question the first ionization potential of nitrogen and oxygen is given. First value should be higher, second value should be lower. First value higher, second value is lower. So this is the correct answer. And here both are equal. Here this is greater, that is for oxygen. Here both are again equal. So this is the correct answer. So answer A, option A is the correct one. Next we will move on to next question. The element with the highest first ionization potential is. Again, all the elements belong to second period. They are in the order boron, carbon, nitrogen, oxygen. According to the general trend, ionization potential increases from left to right. So, according to the trend, this should be the order, but nitrogen is having half filled orbital, which is stable. So this is having more energy than that of oxygen, or among all these, all the four, nitrogen is having highest first ionization potential. So this is the correct answer. So answer C is the option. Which of the following is the smallest in size? The options are N3 minus, F minus, O2 minus and Na plus. Now, all these are isoelectronic species. Atomic here 10 electrons, 10, 10 electrons, 10 electrons. Now, as the atomic number increases, here 7 atomic number, 7, 9, 8, 11. As the atomic number increases, ionic radius decreases. So, the correct answer is Na plus is the correct answer. Answer is D. Next, we will move on to which of the following has largest ionic radius. We will see the options. Largest ionic radius. Now, here 10 electrons, here 10 electrons. These two are isoelectronic species. Here it is atomic number 3, 5. Among these two we have to check, and as the negative charge increases, size increases. So, largest size is oxygen. C is the correct answer. We will move on to the next question. The electronegativity of the following elements increases in the order. We will see the option. So, we have 4 elements: carbon, nitrogen, silicon, phosphorus. Now, carbon and nitrogen occur in second period, silicon and phosphorus in the next period. Below carbon, silicon comes, below nitrogen, phosphorus comes. Now, the electronegativity, as we move from left to right, what happens? Electronegativity increases. From top to bottom, decreases. So, electronegativity of this is more than this, whereas electronegativity of carbon is lesser than that of silicon. So, the order is carbon, order is silicon, phosphorus, carbon, nitrogen. This is the correct option. Silicon, phosphorus, carbon, nitrogen is the correct order. Answer option C is the correct one. We will move on to the next question. The uncertainty in momentum of an electron is 1 into 10 to the power minus 5 kg meter per second. The uncertainty in its position will be, we have to calculate the uncertainty in position. Uncertainty in momentum is given. So, delta x into delta p is greater than or equal to h by 4 pi. This is the formula from Heisenberg's uncertainty principle. So, uncertainty in momentum is 1 into 10 to the power minus 5. This is to be calculated, which is h value is given 6.62 into 10 to the power minus 34 by 4 into pi is 22 by 7. Now, on simplifying this, delta x is equal to or greater than 6.62 into 10 to the power minus 34 into 7 divided by 4 into 22 is 88 into 1 into 10 to the power minus 5. This is taken to the other side. Now, we will simplify this. 10 to the power minus 5, if we take to the numerator, this becomes 10 to the power minus 29. These two together becomes 10 to the power minus 29, whereas 88 this is 6.62 into 7, which comes around 42. 42 divided by 88 into 10 to the power minus 29. This is nearly half of this. So this is 0.5 something we get. 0.5 is something we get into 10 to the power minus 29. Now we'll check the options. 0.5 means here in either this or this. Out of these two we have to check, get the first correct answer. 5 point means, now the power is 10 to the power minus 27. If we are moving to the right side, this becomes 10 to the power minus 30. So the option is C. C is the correct answer. Here it is 28 minus 28. This is correct one. 5.27 into 10 to the power minus 30. So the easier way is on number line. If you go to the right side, you get positive integer. While writing scientific notation, if you go on same side, you should have negative integer. So 10 to the power minus 29 becomes 10 to the power 30. Answer C is the correct one. We'll move on to the next question. Number of electrons present in d orbital. Now while selecting the answer, you should be very careful. We'll check the options. It is 2, 6, 10, 14. Now since it is orbital, answer is 2. If it was subshell, then the correct answer is 10. Now since it is number of electrons in d orbital, A is the correct answer. Next question is, the first ionization potential of sodium is 5.1 electron volt. Now first ionization potential means sodium, from sodium atom we are removing one electron, outermost electron, so that we get Na plus ion, and ionization potential for this is 5.1 electron volt. The value of electron gain enthalpy of Na plus, that is electron gain enthalpy is to add one electron to Na plus ion, the value is exactly reverse of this is exactly reverse of this equation. So delta H value will be same with opposite sign, that is minus 5.1 electron volt. We'll check the answer, and minus 5.1 electron volt is on option C. So C is the correct answer. We'll move on to the last question. The energy of an electron in the nth Bohr orbital of hydrogen atom is, nth Bohr orbital of hydrogen atom is, the options are, here we have n to the power 4, n to the power 3, n to the power 2, n. So this is the correct answer, minus 13.6 by n square electron volt. Answer is correct. So option C is the right option. Now these are the few questions from previous year question paper. Solve more questions. Go through the concepts clearly. If you have thorough idea of the concepts, you can solve any type of questions. Thank you.